morning, all of you. Today, I, Rakhi Sharma, Assistant Professor in Akgec Engineering College, is here to present my topic, particularly to explain one of the complex topic of EDC, which is the Hall effect. These are the outlines that we are covering in today's lecture. First of all, the discovery of this Hall effect, the basic phenomena governing this Hall effect, the whole experimental setup of this phenomena. Finally, the significance, why we are using this, what is its significance, all these things that we are discussing in today's lecture. And finally, the applications. So, the Hall effect is first observed by Edwin Herbert Hall in 1879. Particularly, he belongs to the Johns Hopkins University, and he is the first one who observed this effect in 1879 and was discovered 18 years before the discovery of the electron. So that's all about the history, and the Hall effect was first invented or discovered by Edwin Herbert Hall. Next, the basic introduction, or we can say that what does this Hall effect signify? Basic phenomena. So if we want to define what is Hall effect or how we define it, particularly we are giving the basic definition of Hall effect. So in this we consider a semiconductor bar material. If it is placed in a transverse magnetic field B, then an electric field is induced which is perpendicular to both B and I. What is I? I is the current that is flowing through your semiconductor bar, and B is the magnetic field in which you have placed that semiconductor bar. So the magnetic field that is induced, we are naming it as the electric field which is developed across the semiconductor bar, and this whole effect of generation of the electric field that is induced across the semiconductor bar is known as Hall effect. Due to this induced magnetic field, the voltage is developed across the semiconductor bar, and we term that voltage as the Hall voltage. It is the most convincing method because it helps in determining the type of the semiconductor material, and it also helps in determining the carrier concentration. As if the material is N-type, then the majority charge carriers are the electrons, and if the semiconductor material is of P-type nature, then the majority charge carriers are the holes. So basically, by using this method, we can easily determine the carrier concentration in terms of the number of holes and in terms of the number of electrons, whatever be the majority charge carriers. So by using this method, one of the advantage what we are getting is that we are able to determine the carrier concentration, and the second one is that we are able to find out the type of the material, semiconductor material, whether it is of N-type or whether it is of P-type. So that's why it is the most convincing method that we are using for determining the nature and the type of semiconductor material. This is all about the whole experimental setup in which we are measuring the Hall voltage, which is one of the purpose of using this experiment. What we are in this experiment we are seeing is that if we are placing a semiconductor bar which is having a width V is placed in a transverse magnetic field B, then an electric field is induced which is perpendicular to both B and I, and due to this induced electric field, the Hall voltage is developed across that semiconductor bar, and we are measuring this Hall voltage for the purpose of determining how much electric field is set up across that semiconductor bar. So whatever in this experiment, whatever is going on is we are discussing is that if the semiconductor bar is carrying a current I and is placed in a magnetic field in the direction X, so the electric field that is along the X direction is Ex, that is the electric field that we are getting in X direction is Ex, and the magnetic field is applied in Z direction, that is Bz. So whatever the electric field is induced, we are naming at Ey, that is induced in the downward direction. So due to the induction of this electric field, the holes, or we can say that the majority charge carriers accumulate at one side of the semiconductor bar. Due to this accumulation, whatever the which majority charge carriers are accumulating, due to this accumulation, we are able to determine if holes are accumulated, then we are naming it as p-type semiconductor. If electrons are accumulating at one side of the semiconductor, then we are saying it as a n-type semiconductor. So this is all about the experimental setup that we set to determine the Hall voltage across the semiconductor bar, and particularly to determine the nature, which is whether it is of p-type and whether it is of n-type. The one of the parameter that we determine by using this effect is the Hall voltage. As I described earlier, Hall voltage is basically the voltage that is developed across your semiconductor bar after the induction of induced magnetic field in the y direction. So how do we calculate it? By using this Hall effect, or what is the mathematical expression that I have derived in this slide also. So basically, first equation is signifying is that the electric field is exactly balancing your magnetic field. As electric field is set up, it will exactly balancing your magnetic field, and that magnetic field that is developing, we are naming it as Lorentz force. And this Lorentz force is particularly defined in terms of the drift velocity, which we are saying as QVB or EVB. That is the product of magnetic field with the drift velocity. And finally, it is multiplied with the electron charge. So what we are getting in first equation is that the electric field is exactly balancing your magnetic field at the thermal equilibrium condition. So first equation is signifying the condition of thermal equilibrium in which we are balancing our electric field with the magnetic field. Now, what VH or electric field that we are, Hall voltage we are getting is that the electric field that is induced, particularly in y direction, we are naming it as EH, that is multiplied across your width D. By multiplication of this, we are getting the Hall voltage. The second equation is simplifying the value of this Hall voltage in terms of width of your semiconductor. Next, on moving further, what we are getting, if we are obtaining the current density, simply the current density is defined as the ratio of I by A, that is the current flowing per unit area. So we have defined the current density, and finally putting all these values of equation 1, 2 and 3, finally putting these values in equation 2, we get the value of VH, that is signifying your Hall voltage. And ultimately what we get, VH is equal to the product of B and I, and to the ratio and inversely proportional to the ratio of the charge density and the width of the semiconductor. So this is the final expression that we are getting in case of VH, that is the mathematical calculation of Hall voltage by using this Hall effect. So this is one of the parameter that we get after implementing this Hall effect. The next parameter that we can easily calculate by using this Hall effect is the Hall coefficient. So Hall coefficient is getting in terms of the electric field intensity that is induced across your semiconductor bar, and the final expression that we are getting of Hall expression is of that Hall coefficient is equal to 1 by NQ, or we can say Q or E. Q and E are the same thing, that is signifying the charge of the electron, which is equal to 1.6 into 10 raised to the power minus 19. So the value of RH that we are getting after simplifying our equation is that 1 by NQ, that is signifying for the N-type semiconductor, and particularly RH will definitely change for P-type, and the value of RH in case of P-type will be equal to 1 by PQ. The most important thing that we have to remember is that in case of N-type semiconductor, the value of RH will be negative. That is, it is signifying that the majority charge carriers that are accumulating at the one side of the semiconductor are particularly the electrons. That's why the value is of RH is negative in case of n-type semiconductors, and this value is positive, which we are saying that RH is equal to 1 by PQE or 1 by PE. That is, we are getting positive value for p-type semiconductors. These are particularly the final expression of RH that I have already depicted in the slide. And particularly what is these terms are signifying, EY, that I already told earlier also, that is the electric field that is induced in the y direction. We can also termed it as Hall electric field. And due to this induction, we are getting this Hall voltage which is developed across your semiconductor bar. VH is the Hall voltage, Jx is the current density of the charge carriers. Particularly, if it is of n-type, then the nature of the charge carriers are electrons. If it is p-type, then the majority charge carriers are the holes. Vx is signifying your drift velocity, particularly in x direction. Bz is the magnetic field in z direction. Ix is the current that is flowing through your semiconductor bar, particularly in x direction. W signifying the width of the conductor. T is the thickness. N are the majority charge carrier. Whatever they may be, they are maybe either electrons or holes. And E is finally the charge. E or Q is the charge of the electron. So this is all about the calculation or the final expression that we get for the Hall coefficient after performing this experiment. So what is the significance, why we are using this effect, and why it is considered as the most important method, particularly in semiconductor devices or electronic devices? Because the first important contribution, important thing that we are getting after implementing this effect is that we are able to determine the nature of semiconductor. By nature, we can say that whether it is of p-type or whether it is of n-type. If the majority charge carriers are holes, then it is of p-type. If the majority charge carriers are the electrons, then it is of n-type. So by using this method, we can determine the type of or the nature of the semiconductor material. The second point is that we can determine the carrier concentration. Carrier concentration, we are saying that in terms of number of free electrons, that is N. In number of concentration of number of free holes, that is P. So by using this method, we are able to calculate this number of carrier concentration in terms of N and P. Next point, by using this method, we can able to determine the Hall coefficient, which is one of the most important parameter. And the last, Hall voltage can also be determined by using this method. So these are all the significance, or we can say the outcomes of after performing this Hall effect. That's why it is the most important topic, we can say that, or the most important method, which is widely used in particularly in all the semiconductor applications in designing the ICs. This effect is observed in almost all the IC applications. Because by using this, we are able to calculate many parameters and also determine the carrier concentration and able to categorize which is of n-type and p-type. For example, if you are given a semiconductor bar and we don't know the nature of it, so how we can able to determine if it is of n-type or if it is of p-type? So by applying this effect or by using this experimental setup, we can able to determine its nature and categorize it in p-type or n-type. So this is all about the significance of using this Hall effect. Finally, these are the applications where this Hall effect is being observed and being used. First of all, it is widely used in magnetic field sensing equipments. All the sensors, we are observing this effect. Second one, it is used in phase angle measurement. And finally, it is used in proximity detectors. So this phenomena is used in many applications, in wide range of applications, and that's why it is considered as the most important topic particularly, or the most important method particularly for electronic devices. So that's all about. Thank you so much. So what we have at the end, I would like to summarize all the things that we have discussed so far. What we have discussed, first of all, we have I have given the basic introduction. What is Hall effect? How this phenomena is taking place? What is its experimental setup? How do we, by using this setup, how do we measure certain parameters? What is its significance? Why we are using the Hall effect? And finally, we have discussed the applications of the Hall effect. So, thank you. Thank you.